Complex circuits are circuits that have both series and parallel elements in them. To give an example of how you might work with those, I've got two problems here that we're going to go through. The first one is appropriate for both Regents and AP, and it's sort of a brute force math attack on what the currents and voltages might look like and how you would figure those out. The second problem uses light bulbs and their brightness and dimness in order to interpret what's going on in a circuit. We're going to go through the reasoning on that, which is very appropriate for Regents. Then we're going to back up that reasoning with the math, which is more appropriate for AP. Regents, you can follow along with that anyway and still get the general idea, and you'll have a better understanding of how these work. Okay? So let's get to it. So suppose we have a circuit that consists of a 10 ohm resistor in series with a pair of 10 ohm resistors that are in parallel with each other. To tackle this type of combined circuit, the first thing you need to do is find the equivalent resistance of the entire circuit. So let's do that. Those 10 ohm resistors in parallel can act like a single resistor with an equivalent resistance we'll call RP. 1 over 10 plus 1 over 10 equals 2 over 10. Take the reciprocal, we get 5 ohms. Now 10 ohms and 5 ohms in series act like a single resistor with a resistance we'll call RS. And of course 10 plus 5 equals 15 ohms. This is the so-called equivalent resistance of the circuit. The next step is to apply Ohm's law to the circuit as a whole in order to find the total current. I equals V over R, 10 volts over 15 ohms is 0.67 amps. That's the amount of current coming out of the battery. Now apply Ohm's law to each of the circuit elements to find their potential drop. Use the total current and the resistance of that section of the circuit. To get the parallel voltage, you can use Ohm's law, or you can use the loop rule and subtract the series voltage from the total to get the parallel voltage. Same answer either way. Applying Ohm's law again gives us the current through each parallel resistor, which is half of the total current, just as it should be, because these are equal resistors. And there you have it. To mathematically break down a complex circuit, you first find the equivalent resistance of the entire circuit, then the total current, then you apply Ohm's law a whole bunch in order to find everything else you need. Let's move on to another problem that we can tackle qualitatively first for both classes, and then with math for the AP class. This circuit is going to use light bulbs, which are going to be brighter if they're expending more power. So we're going to have to include the concept of power along with what we just did in that other circuit. And we're going to put in a switch here so we can change this from a series circuit with 2 resistors to a combined circuit with 3. The question is, what happens to the brightness of each bulb when you close the switch? Let's take a look. When the switch is open, it's as if this path isn't here, so let's get rid of it. Now, it's pretty obvious that these 2 bulbs are going to be at the same brightness, right? They have the same resistance, they have the same current flowing through them, and each is getting half of the voltage from the battery. What about when the switch is closed? The current splits through the parallel branch, so each of those resistors only gets half of it, while the resistor in series gets all of the current. So it should be very clear that the resistor in series is brighter than the other 2, which are of equal brightness because they're of equal resistance. The math on this is appropriate for both classes, so let's take a look. With the open switch, it's super easy. The resistor on the branch with the switch gets no current, so it generates no power. The resistors otherwise have a power equal to I squared R, they have the same current and the same resistance, they will be the same brightness. When the switch is closed, the series resistor gets all of the current, while the parallel resistors only get half. Because power is equal to I squared R, squaring that current gives you 1/4 the power. They're going to be significantly dimmer. So here's a harder question. When you close the switch, obviously bulb 2 goes from off to on. But what about the other 2? Does bulb 1 get brighter or dimmer or stay the same? Does bulb 3 get brighter or dimmer or stay the same? Think about it in terms of power. You have 3 equations, and I think I squared R is the easiest. When the switch is opened, you have 2 bulbs in series with a total resistance of 2R. Ohm's law gives us the total current I equals V over 2R. Plug that into P equals I squared R, and you get V squared over 4R for the power of each bulb. When you close the switch, the equivalent resistance becomes R plus half R, or 3/2 R, rather than the previous 2R. So you can already see that the current is going to drop. But let's do that math. I equals V over R, so V over 3 halves R becomes 2V over 3R. Plug that into the power formula and you end up with 4/9 V squared over R. And as 4/9 is greater than 1/4, bulb 1 gets brighter. So what about bulb 3? When the switch is open, the current is V over 2R, which we found before. Use that to calculate power and you get 1/4 V squared over R. When the switch is closed, the current is 2/3 V over R, which we found before. And we can plug that in for power. But wait, the current splits and only half of it goes down each path. We have to divide that by 2 and then plug it into power, getting 1/9 V squared over R. 1/9 is less than 1/4, so bulb 3 dims. Another way to think of this is that before the switch is closed, bulb 3 is seeing half the voltage of the battery. But after the switch is closed, the voltage across the parallel section goes down. It's only seeing 1/3 the voltage, so of course it's going to get dimmer. So there you have it. If you want to do the math on a complex circuit, your first step is always to find the equivalent resistance of the circuit. Combine things together until you have just one resistance, and then you use Ohm's law like crazy all the way through. If you want to figure out things like brightness, you then also have to apply the power equation. Usually power is I squared R is the best choice, but in other situations you might choose to use something else. See you next time.